We're going to start off with what is grab sampling. So grab sampling is known by a lot of different names. Spot sampler, lab sampler, field sampler, or just sampler. But all of these terms are really just different words for the same thing, which is taking a sample from the process pipeline or a tank or something else, and then taking it to a remote lab for analysis. So this analysis is a qualitative measurement. It determines the nature of the sample, as opposed to a quantitative measurement, which would be measuring process variables like pressure and temperature. There are a lot of different styles of samplers, but we categorize them into two broad categories. We have cylinder panels, which is for sampling gases and volatile liquids, and we have bottle panels for sampling non-volatile liquids. So there are a lot of reasons why we might want to or need to take a sample. And the biggest reason is to verify that the product in the tank or what's flowing through the pipeline meets your internal specification or maybe your customer's specifications. This can be at the final state or at some intermediate point in the process. Grab samples are also frequently used with online analyzers. So anytime you have an online analyzer, chances are you're also going to have a grab sample panel so that the results from the analyzer can be periodically compared against the lab results. Anytime you have a change in product custody or ownership, like offloading from a ship to an onshore installation, or possibly flowing out of a chemical plant or a refinery into a pipeline, you will likely have grab sampling so that the product being provided can be analyzed. Very often that sample won't be analyzed immediately, if at all, but the sample will be put on the shelf for future reference if you need to go back and evaluate something. And then finally, samples are often required to demonstrate that certain emissions requirements are being met. And this is done by sampling flare gases and sometimes at other points throughout the process. So there are lots of places within a facility where a sample may need to be taken. Certainly at the storage facilities, such as the tank farm, the storage tanks, both the incoming and outgoing products are sampled. You can also find grab sampling on long transport lines between units and process lines at various points within units. Environmental concerns are also a big driver. We just mentioned the flare for monitoring emissions, but in some cases, the ambient air might also be sampled to detect leakage and for health and safety reasons. And then finally, we already discussed how online analyzer installations will likely include one or multiple grab sampling points. So we keep talking about grab sampling and online analyzers. So let's look at some of the advantages and disadvantages of grab sampling as they relate to online analyzers. There are some definite advantages that grab sampling has over online analyzers. First of all, grab sampling is less expensive. Grab sampling panels can be complex, but the majority of them are pretty simple. And because of their simplicity, they're relatively easy to install and maintain. Also, because of their small size, they can be installed very close to the sample tab. This is unlike online analyzers, which normally they have to be installed inside of a shelter. And these shelters they can be quite large. It can be difficult to find a location inside of a crowded facility to locate the shelter as well. So as a result, these shelters can sometimes be very far away, 100 meters or more away from the sample tab, compared to that grab sample panel that's usually within a few meters. And then you got to think about the installation cost of all that tubing to get from the tap to that analyzer shelter. Finally, having online analyzers scattered throughout a facility means that your analyzer technicians have to be traveling throughout the facility to troubleshoot and to maintain those analyzers. Using grab sampling instead, it allows those analyzers to all be located in a central lab and allows that expertise to be concentrated in one place. Of course, grab sampling also has several disadvantages when comparing them to online analyzers. And the number one disadvantage is time delay. With online analyzers, the gold standard for time delay is 1 minute or less. And that's 1 minute to transport the sample to the analyzer and get your results, which is essentially a real-time result that can be used to adjust the process as necessary to keep the production within the given specification. So with grab sampling, that's not the case. Sure, you can get the sample from the process to the sample container in 1 minute, but how long does it take to get that sample back to the lab? And then once it's at the lab, how long does it sit in queue before it actually gets analyzed? Now, under normal circumstances, the best case with grab sampling is 1 to 2 hours, but sometimes it's much, much longer. And what happens if a sample was taken 12 hours ago and just now gets analyzed and is determined to be out of specification? Have you just produced 12 hours worth of bad product? Something to think about. And another disadvantage is that with grab sampling, it's more difficult to maintain the sample at its process conditions, the right pressures and the right temperatures. And this can lead to phase changes and sampling inaccuracies. As we're going to talk about later, if the sample changes phase, then the sample can be fundamentally altered, which is not what we want. With grab sampling, by its definition, you're introducing a human element. Without automation, which is rare, there's a human involved when you extract the sample from the process. That means there's the potential for exposure, spills, or another accident. Therefore, grab sampling is fundamentally more dangerous. And lastly, we've seen where customers have failed to adequately clean out their sample containers, and this can lead to samples that are contaminated by the remnants of the previous sample taken in that container. Now that we have some background on grab sampling, let's discuss some of the basic principles that we use when designing a grab sampling system. So when we are designing these panels, we want to keep a number of things in mind. First of all, we want to make sure that the sample extracted from the pipeline is representative of what is actually flowing through it. As a result, the preference is to use probes so that we can sample from the center of the pipeline instead of along the wall where there can be contamination and sediment. We also do what we can to limit phase changes to avoid changing the sample. We also want it to be timely. It's not as important as with an online analyzer, but there's no point of getting the sample to your container in 1 minute or less if it's going to sit around for hours before it's actually being analyzed. But we do need to understand the time delay and make sure that our transport time is measured in minutes, not hours or not in days. Purity is also a concern. Dead legs are a major source of contamination that we can avoid. See the system shown here in the picture. So in this system, the inlet is at the top left and the sample is flowing to a sample container off the bottom of the screen. However, this system has 2 dead legs. And a dead leg is defined as an area of no flow that can contaminate the sample flowing by. So here in red, you can see those dead legs. You have a short length of tubing leading to a bypass valve and a pressure gauge. You can see how there would not be any flow in these areas, and without flow, there's going to be old fluid that just sits in there permanently. As the fresh sample flows down our green path, molecules from the red sections make their way into that sample flow and they contaminate it. So to avoid these dead legs, we want to either minimize those lengths of tubing, or best case is to eliminate them altogether by moving them downstream of the sample container, where it won't matter if the molecules leak out into the main flow. This is why we always try to put gauges, flow meters, and other instrumentation products downstream of the sample container where they cannot cause a dead leg. Flush time is also an important concept with these systems. So flush time is the amount of time required to flush all of the old fluid out of the supply line so that we can get a fresh sample into our container. Simply put, it's a measure of the amount of time it takes to get the sample from the sample tap to the sample container, and is a function of the flow rate, the system volume, including the volume of the transportation lines leading to the panel, as well as the volume of the panel itself. So in order to make sure that we take a fresh sample, we need to let the panel flow for this flush time and then take our sample. On a dead-ended sample panel, where we're not returning the flow to the process, this can be a challenge. So what do you do with the old sample that gets flushed out? Some customers will flush it into a bucket or maybe another bottle or another sample container. But the better solution is to use panels with a continuous flow. With a continuous flow panel, the transportation line to the sample panel is always flowing and is then returned to the process, which has two main advantages. First, it reduces that flush time all the way down to 0. And there's always going to be a fresh sample at the sample panel because the lines are always flowing. Second, because we are returning the flow to the process, we don't have to worry about disposing the flush fluid. Now, flushing and continuous flow should not be confused with purging. Purging is different. With purging, we're taking a secondary fluid. Usually it's an inert gas like nitrogen, but it could also be a solvent or something else, and we're flowing it through the sample panel to clean it out. There are two main reasons why somebody would want to purge a grab sample panel. First is that the sample could be toxic. So when you have a highly toxic sample, before disconnecting any quick connects or breaking the system, you would want to purge the lines. That way, any spillage that occurs while uncoupling those quick connects would be the purge gas, not the toxic sample. And then secondly, the sample could be a warm liquid that, when allowed to cool, will solidify and could possibly plug the lines. Purging out the lines removes that old sample and prevents that from happening. Of course, when we're designing these systems, safety is always one of our highest priorities. Since there's a person involved with the sample collection, we need to make sure that the sampling system is safe. One way to do that is to make sure that the operator knows what they're doing and how the panel operates. A simple way to address this is to make sure that operating instructions are listed at every sample point and that operators are trained to those procedures. Another important aspect of safety is selecting the best sample container. For a sample that's toxic to either the operator or the atmosphere, a sample cylinder is a much better choice because its leak integrity and its rugged nature. Compare that to a bottle. A bottle, there's possibility for leaks through the pierced septum or around the cap and the threads. There's also the possibility that a bottle could be overfilled or even broken. There's no such concerns with the sample cylinder. So, which brings us to our next big decision. What type of sample container do you need? Again, two main choices, bottles or cylinders. But how do you select the right one? Well, we've already discussed one consideration, and that's toxicity. So for toxic samples, a cylinder is definitely preferred due to its higher leak integrity. But there's other factors to consider as well. So for example, a sample cylinder is definitely more expensive than a bottle. So we want to use bottles wherever practical due to financial considerations. But bottles do have some limitations. One is that bottles are not pressure containing. That becomes critical when we have a volatile liquid sample. And a volatile liquid is one that wants to vaporize at atmospheric pressures and temperatures. So in order to keep it from vaporizing, you need to keep it under pressure, which is not possible with a bottle. So you must use a sample cylinder. But a bottle can be used for non-volatile liquids. And one way to understand if a liquid is volatile is to look at its vapor pressure. So that vapor pressure is the amount of pressure required to keep that sample from vaporizing at a given temperature. And in order for the sample to be considered non-volatile, well, the vapor pressure must be at 14.7 psia, 14.7 atmospheric pressure or below. So it's important to keep that volatile liquid from vaporizing, because if you vaporize the sample, you can change the sample. In the same regard, we want to avoid condensation in a gas sample. So what we do is we really need to understand how our sample is going to behave at different temperatures and pressures. And to do that, we need to understand the phase diagram for the sample. So the phase diagram shown on the right is a plot of the different phases of a substance as they relate to temperature and pressure. So using the phase diagram for a given temperature and pressure, we can see that phase, whether it's liquid, gas, or solid, that we should expect to have. It also helps us understand how changes in temperature or pressure can affect the sample. For example, let's say we have a liquid sample that's under pressure at a given temperature, and then we allow the pressure to drop. So you can see how the sample would want to change from a liquid to a gas. And if you have a mixture of components, maybe only the lightest components will vaporize. Now you've changed the sample and you might not ever be able to get it back to the way it was. So in general, increasing the temperature or decreasing the pressure will cause the lighter components to boil or vaporize out of a liquid sample. Decreasing the temperature or increasing the pressure on a gas sample will cause those heavier components to want to condense out. So in order to maintain the representativeness of the sample, we want to avoid this phase change by maintaining the sample at the process conditions wherever possible. So to illustrate the point of sample volatility, let's look at an example with a distillation tower, which is the central process in the refinery. So crude oil is piped into the boiler, where it's boiled off into gases. The hot gases then rise through the tower, and depending on their density and their boiling points, they're going to condense out at different levels in the tower. Of course, at all these different outlet points in the tower, you're likely to have grab sampling. At the bottom, you have heavier liquids like fuel oil and other components that never even boiled off in the first place. And because these are non-volatile liquids, they're likely to be sampled in bottles or even metal cans. At the top of the column, you have the gases, like methane, that never condense. Because those are gases, they would be sampled using a sample cylinder. But in the middle of the tower, you have some volatile liquids. And because they're volatile, we have to keep them under pressure to keep them from vaporizing. Since bottles are not pressure containing, we have to use sample cylinders for these volatile liquids. So let's look a little bit more closely. Here we see a list of hydrocarbons that might be extracted at different levels of that tower. So for determining our sample container, we're most concerned with the fluid's volatility. At atmospheric conditions, we would look at the boiling point to determine whether or not the sample will be volatile. In the table, we can see that up near the top, with those that have light components, have a very low boiling point. Down at the bottom, we have the heavier hydrocarbons with the very high boiling points. But it's the ones in the middle that are the most interesting. So let's take a closer look at a couple of them. Here we have pentane, which has a boiling point of 36 degrees C. That's hot, but there's some places in the world where ambient temperature gets up to and may exceed 36 degrees C. Because of that, we would consider pentane to be volatile. Contrast that with the next one on the list, hexane. Here we see hexane has a boiling point of nearly 70 degrees C. There's nowhere on Earth where we're getting up to 70 degrees C, at least not yet. So we would consider hexane to be non-volatile. So this is where we would draw the line between hexane and pentane. Anything above the line is either a gas or a volatile liquid, so we would want to use a sample cylinder. Anything below the line would be non-volatile liquid, and we could use a bottle if we wanted to. So if we're going to use a cylinder, there's a few basic rules to follow. There's some debate about whether a cylinder should be oriented horizontally or vertically. It's our stance that orienting the cylinder vertically is the best practice. So when sampling a liquid, we would typically fill from the bottom up. And when the cylinder is mounted vertically, filling from the bottom up allows the gases to escape out the top of the cylinder as it fills and ensures that you get a full cylinder. Conversely, when sampling a gas, we typically fill from the top down, which would allow any condensation to be flushed out the bottom instead of collecting in the cylinder. When using a sample cylinder, we also need to be concerned about overpressurizing that cylinder. So with liquids, a common way of doing this is to use an outage tube. The outage tube shown here on the right creates a vapor space that helps to protect the cylinder from overpressurization due to the thermal expansion of the liquid. Without that space, the liquid, which is incompressible, would have nowhere to go if it is expanded due to some sort of rise in temperature. There'd be a chance that the cylinder could rupture. However, including this vapor space with an outage tube, there's a place into which the liquid can expand. It will compress the vapor space, which increases the pressure slightly, but this is not as severe as a pressurized as with a cylinder that was 100% liquid full. But with gases or liquids, a rupture disc or a relief valve or other methods of protecting the cylinder from overpressurization. However, it should be noted that rupture discs and relief valves should not be used with toxic samples to help keep our operators safe. When sampling in a bottle, it's most common that the bottle will have a rubber septum built into the cap. So to take a sample, the septum is pierced by a pair of needles, a fill needle and a vent needle. On the left, you can see these needles and the caps with the rubber septum. So the samples will be dispensed into the bottle through the fill needle, and then the gases that are in the bottle can escape out the vent needle as they are displaced by that incoming liquid. This flow of sample is typically controlled by a sampling valve, as is shown on the right. This valve with the needles affixed to the bottom, it provides a means of turning flow on and off. It also usually includes a shroud that helps to guide the bottle into the needles and holds and protects the bottle during the sampling operation. And these valves are sometimes used without a shroud, but that's not recommended, because if you don't have a shroud, the needles are exposed and it creates a potential safety hazard. Additionally, without the alignment provided by the shroud, the needles are more likely to be bent when pushing the needles through the septum. The size of the needles will vary depending on the application. In general, it's best to use the smallest needles that will work for the application, because smaller needles will create less wear and tear on the septa. However, larger needles may be required for sampling with those higher viscosities, or if there's large solid particulates in the sample, you may need to go with a larger needle. Smaller needles are more susceptible to accidental bending, which makes it important to use sampling valves that have replaceable needles, because bent needles are the #1 maintenance item on these sampling valves. And then lastly here, the last best practice for bottle sampling is there are some concerns with it. Remember, the bottle is not pressure contained. Sampling from high pressure sources can cause problems. Even with a sampling valve to help control the pressure and flow, dispensing a high pressure sample directly into a bottle can potentially damage the bottle and cause a safety concern. Another potential concern is overfilling and overflowing the bottle. If the operator is not paying attention and does not close the sampling valve at the proper time, the bottle can overflow and create a potential safety or environmental hazard. In the picture here, we can actually see evidence of overfilling a bottle. The dark spot on the ground under the sample valve, just right here, is where some of the sample was spilled. Fortunately, both of these issues have a common solution, which is to implement what we call a fixed volume sampler. So with a fixed volume sampler, a predetermined amount of fluid is measured out, and then it's transferred into the sample bottle using a low pressure purge gas. With the pre-measured liquid, there is no possibility of overfilling or overflowing the bottle. And because we are using low pressure purge gas to push the sample into the bottle, we've isolated the bottle from the high process pressure. So I hope you enjoyed the insight there. We talked about what is grab sampling, which different bottle or container to select, and then some best practices around both. So at this point, we'll take any questions. And then if not, our July Tech Talk is going to be around mechanical seal support, where we're going to discuss how do you protect the rotating equipment in your plant, specifically those mechanical seals. So be sure to join us next month, Wednesday, July 21st. We'll be discussing that topic. Thank you.